we're going to look at a more complex fault tree. We have an hydraulic pump that does not start, and this is our top event. And it is given by four primary events: a power supply failure, a pump mechanical failure, a control system failure, and fluid issue. So these are the four primary events, which then obviously develop further. In a previous example, we in fact consider the power supply failure. In a previous video, we considered the power supply failure, which was given by three base events: non-electrical power, faulty wiring, and motor failure. Now we decided to explore a little bit more, and we found what are the potential causes leading to a no electrical power, or what are the causes leading to a faulty wiring or to a motor failure. And this is how we developed with the various causes. In some cases we had to go one further down, like for example motor failure was given by motor winding burnt and thermal overload, and we found that thermal overload was given by overheating and a thermal relief valve failure. So in this case we've introduced another gate. We've introduced the AND gate, and in this case, to activate the AND gate, both events have to occur. So both overheating and thermal relief valve failure have to occur. It doesn't matter which order, they don't have any priority. It doesn't matter which order, but as long as both of them occur, then we'll have an activation of this AND gate. The same thing cannot be said for what is next to them, which is this type of AND gate, but it's called a PAND, or a priority AND gate. And the priority AND gate, it first of all is a dynamic gate, different from this AND and OR, and it requires two events to occur. Like in this case, we got excessive temperature and fluid oxidation and degradation, but they have to occur in a specific sequence. If they occur in, say for example, in this case, excessive temperature have to occur, and then fluid oxidation and degradation has to follow. If they occur the other way around, then the PAND gate will not be activated. And then as we scroll along, we've also got some undeveloped gate, and we can see those here. This is an undeveloped event. We could have explored it further. We decided just not go any further, so we just labeled it with this type of diamond. And as I say here, we got another type of symbol. We got this sequence enforcing gate. Again, it is a dynamic gate of a fault tree, and is a combination of three events which have to occur in as the name suggests, sequence enforcing in a specific sequence. In this case, a sill damage has to occur first, which then leads to a contamination, dart, ingress of moisture or dust into the system, into the hydraulic fluid, which then leads to corrosion, and that results on pitting and rusting, and then brings the bearing failure, which then causes mechanical failure, which then causes the hydraulic failure, and so on. So here we got the full fault tree. And similar to what we've done before, we can just calculate the results, and we can indicate where we want the results. We want it at 1,000 hours, or we want it at a different time, it doesn't really matter. And we see then the results at the top level, 53% probability of failure of our pump at 1,000 hours. And we can also look at some graphs. Before we go into that, we can look at the graphs at system level. So this is the probability of failure of our top event. So the hydraulic pump doesn't start, and we can see how this probability of failure gradually rises as the time progresses. And then we've got reliability, PDF, and failure rate. And we've also got this Pareto chart, which is instead the criticality analysis of the gates. So in other words, it looks at which gate is more critical. The one with the highest Pareto is the most critical, and the color, this beautiful color palette, in reality represents what the reliability is. So here we'll have, for each one of these bean, we'll have in fact two pieces of information. We'll have the reliability at, in this case, 15,000 hours, and we'll have their importance. So this importance is kind of like an index, so to indicate which component is more critical compared to others. And that's it. So these are analytical for 3, in so much that for each block that we analyze, say for example this loose connection, we simply have a failure distribution. We don't have any information about repair distribution. The moment we configure also repair distribution, we change completely the configuration of the fault tree, and it becomes a simulation type fault tree. And that's it.